Exercise 6F, sine and cosine graphs. What we have here is a table of values. We have angle theta, and that's varying between negative 2 pi and 2 pi. And we take those angles and we work out the sine of those angles in this next row, sine of theta, and you can see the values produced here. These values have been produced just using a CAS calculator. So for example, I've literally just put into my CAS calculator sine of negative 2 pi, and that produces 0, and I put that into the table. If I were to take those values and place them on a set of axes, graphically it would look like this. And you can see it's a wave shape, so it's our wave pattern, and it goes on indefinitely towards the right and indefinitely towards the left. If I focus between theta equaling 0 and 2 pi, you can see I begin at the position 0, 0. I then move to the position pi on 2, 1, then back down to pi, 0, 3 pi on 2, negative 1, and then back to 2 pi, 0. So that pattern will go on forever. And in the same way, I can also take a look at cosine. So once again, a table of values. Using my CAS calculator, I can produce the corresponding cos of the given angles. Graphically, it looks fairly similar. It's a wave shape again, but the pattern form is a little bit different. You can see once again if I begin between 0 and 2 pi, in this case I start at the position 0, 1. I then move down to pi on 2, 0, pi, negative 1, 3 pi on 2, 0, and 2 pi, 1. So they are the sine and cosine graphs, and they are closely related to the unit circle. So if we go and take a look at the unit circle, so here I have the unit circle. Remember, it has a radius of 1, and I have a point P. Remember, this point P can be described as being x, y, but equally it could be described as being cos theta, sine theta, where theta is the angle swept in between the ray and the x-axis, so it's this angle in here. Alright, if I now turn on the sine function, you can see here's my sine graph to the right hand side of it. So basically all I've done here is that you've got a vertical axis ranging in this case between negative 2 and 2, and then horizontally what we've got is the angle theta. Now this is given in degrees, but it could easily be in radians, so you can see here 0, pi on 2, pi, 3 pi on 2, and then 2 pi. And I can make this point P move around the outside of this circle, and we can see what sine of that angle theta is equal to. Remembering that if this point P can be described as being cos theta, sine theta, it's quite clear to us that the y value at this point is going to be equal to the sine theta. So you can see in this certain position that whatever this reads off to be on the y-axis of the unit circle is also what's equal to sine of that angle theta, this theta here, which is unknown, or in fact it is known to us, it's 34 degrees. So sine of 34 degrees is equal to exactly 0.5592. So what we're saying with that is that this position along over here where it cuts through would be 0.5592, and that in the same way that sine of 34 is equal to 0.5592. So let's take a look at the animation. So here you can see that the dot is approaching pi on 2, the value of y is approaching 1, there we are, you can see that graph. Now as theta gets towards pi, you can see the value of y is approaching 0. Theta continues and we're approaching 3 pi on 2, and the value of y will be approaching negative 1. It's a sine of that is negative 1, and then we've almost done one full revolution getting towards 360, and we're complete just now, a little bit over, but you can see there that we've done one full cycle of the graph, one full revolution of the unit circle. I can continue on and apply the cosine on top of it, so there's a cosine on top, and let's just take a look at one full revolution of the cosine, one full revolution of the unit circle. Let's turn off the sine and hit start, and you can see the two dots. Of course now we're looking at the x value, so As the p is approaching pi on 2, the value of x is approaching 0. And now p is approaching pi, and the value of x is approaching -1. P is approaching 3 pi on 2. The value of x is approaching 0 again. And as we approach 2 pi, the value of x will be approaching 1. Beautiful. Okay, so that shows you the relationship between the unit circle and the sine and cosine graphs. Going back to our notes, so there's an explanation of that. A couple of really important points for us to understand is the period and the amplitude. So the period is just basically how long it takes for the graph to start to repeat itself. So if we begin from this position here at 0, 0, you can see that we do one full cycle, and it takes us 2 pi radians until the cycle begins to repeat itself. So we can say there that the period is equal to 2 pi. You can see it's a distance, the same distance between the two peaks here. Alright, so here I'm at the peak, and then I finish off at the peak over here, and the distance in between that is 2 pi. The amplitude is just the measure of the size of the wave. Okay, so we don't measure from the trough to the peak, we just measure from what they call the median to the peak. Okay, so the general standard form is an amplitude of 1. So basic graph, so if we had the basic y equals a sine of nx and y equaling a cos of nx, then the amplitude is a. That's assuming that a is positive. Of course, if a was negative, then it would be just the magnitude of that. So in other words, we're looking at the size of the a value and not the sign of it. The period is 2 pi on n, where n is the coefficient of x. If n is less than 1, the graph is effectively stretched horizontally, so it's drawn out. If n is greater than 1, then the graph is effectively compressed. So we're taking the wave and we're pushing it in tighter. If a is less than 1, the graph is compressed vertically. Okay, so we're looking at, along the y-axis, we're looking at contracting it. And if a is greater than 1, then we're stretching it out. The way that we describe the effect of this is that we say that A we can describe as being a dilation factor of A parallel with the y-axis, that is, it is from the x-axis. So in other words, we take every y value of the points and we multiply it by A. And we say that we also have a 1 on n parallel with the x-axis. So in other words, what we're doing there, guys, is we're taking the value of the x of every point on the original graph and we're multiplying it by 1 on n. Alright, here we have a problem. Sketch the graph of the function. We've got f, given that we go from 0 to 5 pi on 3. Notice it's circular bracket, so that means that we're not including where x is equal to 0, but we are including 5 pi on 3 because we have the square bracket. So the domain is between 0 and 5 pi on 3, and we can have any real number that's been produced from this rule here. F of x equals 2 lots of sine of 2x on 3. And we have to state the range of the function at the very end. To help us understand that, it's probably always good to work out what the amplitude is. So it's just going to be the magnitude of 2, so that's that number in the front there, which is 2. So it gives us an idea of how wide the wave will be. Sorry, how tall the wave will be. Our period is 2 pi on n. Now n is just the number in front of the x, so we can think of this number as being 2 on 3 times x, so 2/3. So 2 pi over 2 on 3 is the same thing as getting 2 pi and multiplying by 3 on 2, and we see that it's equal to 3 pi. So in other words, one full wave will be completed as theta goes from 0 to 3 pi. That's how long it will take. Describing the transformations is always a good idea, just to get our heads around what's happening. So first of all, it's dilated by a factor of 2 parallel with the y-axis. So that's given from this 2 here. So that just means that every y value on the original y equals sine of x has been multiplied by 2. Also, we see that it's been dilated by a factor of 3 on 2 parallel with the x-axis. So what this tells us is that every x value on the original graph has been multiplied by 3 on 2. Effectively, it's been stretched. When I'm graphing this, I like to use a bit of a T-grid method. So you can see here on the left-hand side, I've put down all the critical values for the basic graph, the basic sine function. So I've got 0, 0, pi on 2, 1, pi, 0, 3 pi on 2, negative 1, and I've got 2 pi, 0. So that's my x's, well they are my x's, and these are my y's. And then I apply the transformations on them. So first of all, a dilation factor of 2 parallel with the y-axis, so I'm getting all these y values, and I just got to multiply by 2, and that will create these values over here. The next transformation I need to take care of is dilation by a factor of 3 on 2 parallel with the x-axis. So I take the x values and I multiply those by 3 on 2 and I get these results. And then it's a matter of placing these down for the x's and this column here for the y's, placing those on a set of axes, and which I've done just here. Whoops, as you can see, just there. So these are the 5 critical points which I've found, and I've placed them, and I get that nice wave shape as I expect. But what I do need to do is take in consideration the endpoints. So first of all, the domain on the left-hand side, I start at 0. So I plug in 0 into the rule, and I get 0, which is not a big surprise. So the point 0, 0, and I notice that because in the original domain, just giving up the top here, in my original domain, 0 is not included in the domain. So I should see a circular point there, a hollow point. Okay, so that's 1 point, that's excluded. The included point is 5 pi on 3, so I substitute 5 pi on 3 into the rule, and I get 2 sine 10 pi on 9, and that point is included. So getting back towards my graph, I've drawn it with the endpoints. Now, you might be sitting there asking, how is it that you know that 5 pi on 3 is somewhere around here between 3 pi on 2 and 9 pi on 4? Whenever dealing with radians in this type of problem, I always try and think of making it easier for me by converting it to a decimal. So 3 pi on 2, for instance, I can think of as being 1.5 times pi. 9 pi on 4, I can think of as being 2.25 lots of pi. And of course 5 pi on 3, I can think of as being 1.67 lots of pi. So 1.67 lots of pi is somewhere between 1.5 lots of pi and 2.25 lots of pi. So I can safely say that it's somewhere along this section. And if you were to evaluate what 2 sine of 10 pi on 9 is, you'll see that it comes out to being a negative number. A really big point here, guys, in this type of question, it's not really critical for you to show all the workings that I have. Okay, what you will be graded on or judged on is how well you've drawn this graph and that you've shown the endpoints. It may be a good idea to show the workings to calculate the endpoints, but at no stage will you be assessed on how well you've set up a table and whether or not you've written down the transformations. It's simply there to help you get to that graph. The graph is what you're looking at with the calculation of the endpoints and the endpoints clearly shown. As you become better at this, then you become more efficient and you won't have to write as many details. But as always, when I provide solutions to problems, I'm doing it in such a way that you can go back into your notes and it'll make sense to you. But a part of the question was asking us for the range, okay? And with our range here, you can see that the lowest value included in the graph that we need is over here. So that lowest value is 2 sine 10 pi on 9, and then the highest value we achieve is 2. So I'm going from 2 sine 10 pi on 9, that's the lowest value, and that ends up being a negative number if you were to get an approximate answer for it, going all the way to 2. And notice that I'm including the 2. All right, so I do actually include this position here. So I am including the 2, and I also include this.